So last time we introduced the concept of continuity. So I want to continue that and finish up the discussion. And remember, continuity is a limit definition. So we say function f of x is continuous at the point x equal to a if and only if the two-sided limit of f of x as x approaches a equals f of a. So it's important to remember that continuity is really a limit property of a function. Then we had some results that told us polynomial functions, rational functions, root functions, and trigonometric functions are continuous on their domains. And also that the sum of two continuous functions is again continuous. The difference of two continuous functions is again continuous. The product of two continuous functions is again continuous. And the quotient of two continuous functions is continuous on their domains. That part is really important, that a function can only be continuous on its domain. Finally, we also have this result that the composition of continuous functions is again continuous. So now we've, got some good theory to justify why many of the functions that we work with are continuous. We also talked about types of discontinuities. Basically any time that limit definition violates, anytime the limit definition is violated, then we don't have continuity. Sorry, I've gotten a message from a student who should be messaging me later, not during class. Okay, so here are the three types of discontinuities we could have. One, if the limit somehow doesn't exist. So here you could have the limit, goes to infinity or negative infinity. So that's the first case here. Or in the third case, where the limit from the left and the right exist, but aren't equal. So there we have scenarios where the function is not continuous. And then the other cases in number two, the limit exists, the limit isn't the issue, the function isn't defined at the point. So any way we can get that equation, the limit of f of x as x approaches a equal to f of a, any way we can get that equation to be violated, we're going to have discontinuity. So I want to do this example now. So the example says, what is the domain of the function y equal to the positive square root of x minus 1 plus 2 sine of x? And then the question asks, is this function continuous? Justified. So the reason I mentioned domain first is, as I said, a function cannot be continuous outside of its domain. So to me, the continuity concept, the concept of domain and the concept of continuity are very connected. So first, let's figure out where this function even makes sense. So for the domain of the square root of x minus 1, for an even root, we cannot take the even root of a negative number. So we need x minus 1 right here under the root. We need this x minus 1 to be greater than or equal to 0, and that's true when x is greater than or equal to 1. And the domain of the trigonometric function sine of x is all reals. And so now to find the domain of the sum, we look at the intersection. You remember this word intersection, it's the common region. So here we're intersecting this 1 to infinity with r. So the closed interval 1 to infinity, that's the domain of square root of x minus 1, and r is the domain of sine of x. And so the common region is the interval 1 to infinity inclusive of 1. So that's our domain. And so now I'm going to explain. So now here's my explanation as to why this function is continuous on that domain. So basically the explanation is to use those theorems that we had before, that the square root of x minus 1 plus 2 sine of x is in fact the sum of two continuous functions. And so now I'm going to discuss why each of the functions is continuous. So square root of x minus 1 is a composition of continuous functions. It's the composition of square root of x and x minus 1. So that's why it's continuous. So we had a result, And the scaled trigonometric function, I say scaled because it's multiplied by 2. You wouldn't have to say that. Here, the trigonometric function 2 sine of x, we know trigonometric functions are continuous according to that theorem. So here we have composition of two continuous functions, which is continuous, plus a trigonometric function, which is continuous. So the sum itself is continuous on its domain. That part is important to specify, where it's continuous. And here, the theorem that tells us polynomials are continuous, rational functions are continuous, doesn't have a name. So we don't necessarily have to shout out the theorem. But in this class now, we know that these types of functions, it's a known fact that polynomials, rational functions, root functions, trigonometric functions are continuous on their domains. Sums of continuous functions are continuous. These are all now known facts and can be used as justification, to answer the question, why is this function continuous? It's really important when you look at a function that you try and classify it. What am I looking at here? Is this a polynomial? Is it a trigonometric? Is it a sum of two different types of functions that are continuous? So that part is really important, to really look at the function and start to analyze it, break it down piece by piece. It's the sum. Now the functions that we're adding together, are they continuous? And you kind of just analyze it piece by piece. This next example, I wanted to talk about the difference between this function here, f of x is x squared minus 9 over x minus 3. And I wanted to compare it with this function x plus 3. So what's going on here? So I think it's a very natural thing in this situation. It's very natural for a student to do the following. Okay, so check out the math I'm about to do here. So I think a very natural, set of math to do for a student is they'll say, well, x squared minus 9, I can factor it as x minus 3 times x plus 3. And in the denominator, we've got that x minus 3. So, doing math, the natural thing now to do is to cancel the x minus 3. And now I conclude, well, this function is basically just the same as x plus 3, that based on this math. And so that's actually not true, So x squared minus 9 over x minus 3 and x plus 3 are actually different functions. And let me show you, let me get into the discussion of how we talk about that. So first of all, I would, again, look at the domain. We know that the denominator can never be 0. So right off the bat, there's a domain restriction on f of x that is not true for g of x. For g of x, there is no domain restriction, right? G of x is a really well-defined function. And so here, for g of x, the domain is all reals. So that right there is one difference. The domain is different. So let's actually see if we could plug in, what is happening at 3? Can we plug in? Can we see what's going on at 3? So with f of x at 3, if we let x equal 3, let me do, if x is not equal to 3, then all of the math we did before works. If x is not equal to 3, then in the denominator here, this is not 0. So all of this math makes sense. This math wouldn't make sense if we were dividing by 0. If x is not equal to 3, then yes, I can factor the numerator, I can cancel, and in fact, when x is not equal to 3, yes, it's true that f of x is the same as x plus 3. If x is not equal to 3. That's the main important thing here. So yeah, if x is not equal to 3, we can do all this math, and yes, f of x and x plus 3 are not different. They're the same function. The difference occurs when x is equal to 3. When x is equal to 3, the function f of 3 is 0 over 0 and is undefined, while the function g of 3 makes perfect sense. It's defined and is equal to 6. And so right here is the big difference between these two functions. In fact, the function f of x, if we take the limit actually exists. So here I have a function where the limit exists, but the function's not defined at the point. So this is exactly when we have a removable discontinuity. The limit from the left and the right exist, are finite and equal the same number, but the function at the point is undefined. So here in the graph, we would have a hole. So here, the limit from the left would be going to 6. The limit from the right would be going to 6. But at the point, it's undefined. And so, another part of this question was, can we redefine it or adjust the function so that it is continuous for all x? So when a function has like one removable discontinuity or finitely many, 2, 3, 4, we can fix the function at those individual points. So here we can redefine, another word that's used is to adjust the function. I don't think our book uses that. Other books use the word adjust. Our book uses, I think, redefine mainly. So we can redefine or adjust the function so that it's continuous for all x in the following way. So when x is not equal to 3, I'm just going to define it to be f of x. There's no problem. So by the way, here I'm defining the new f. That's why I have this subscript new here. This is my new f function. So when x is not equal to 3, just define it to be f of x, because there's no problem away from 3. When x is equal to 3, we fix it by defining the function, the new function, to be 6, where 6 is the value of this limit. So here, remember, the value of f of x as x goes to 3 exists and is equal to 6, then I'm plugging in that value right there. So I'm using this limit here, the value here, down here to fix the function when x is equal to 3. This is kind of an artificial example. Basically, when we fix the function, we've basically defined this new function f just to be x plus 3. Because away from 3, f of x looks like x plus 3. When x is equal to 3, g of 3 equals 6, and basically that's what we've defined f to be. So in this scenario, it's kind of an artificial example. We've basically just defined the new function to be g of x, which is x plus 3. If you compare this function here to g of x, they're identical in terms of inputs and outputs. So the most famous example, I guess, of fixing a function is for the sine of x over x function. So sine of x over x at 0 is undefined. So sine of x over x, if you plug in 0, I get 0 over 0, it's undefined. But the limit exists. We know we can show a squeeze, we can use a squeeze theorem to show the limit as x approaches 0 of sine of x over x is 1. So here I can fix sine of x by defining a new function like this. If x is not equal to 0, define the function. So if x is not equal to 0, define the function to be sine of x. If x is equal to 0, we know sine of x is undefined, but the limit equals 1. So let me redefine, when x is equal to 0, redefine the function to be 1. So this is probably the most famous example of fixing a removable discontinuity by redefining the function at a point. And why is this famous? Because the sine of x over x function is used a lot in applied sciences and in applied math. And you'll see it later on in your career. So this is kind of the most maybe common example of fixing a function that has a removable discontinuity. So another very important result regarding continuity is known as the intermediate value theorem. So here is the hypothesis of the theorem. Suppose f of x is continuous on some interval a, b. That's the first hypothesis, that we have continuities, very important. And now suppose capital N is some number in between f of a and f of b. What do I mean in between? I mean either n is greater than f of a and less than f of b, or n is greater than f of b and less than f of a. So this depends on if f of a is bigger than f of b or if f of a is less than f of b, if you're dealing with like an increasing or decreasing function. So either way, if n is a number in between, so that's the hypothesis. So if you have a continuous function and if n is in between f of a and f of b, then the conclusion is there exists at least one number, c, in the interval such that f of c equals n. So we're saying that if capital N is in the range of a continuous function, then there must be some input value in the domain that'll map to capital N. And here's the picture. It's important to connect the words to the picture. Okay, because that's part of what we're trying to do here in math, is to connect the part of the brain that deals with words with the part of the brain that deals with pictures. So look, here's capital N, and you can see it's in between f of b and f of a. There's f of b, f of a, capital N is right in between. And so the theorem says if the function is continuous, so here you see a nice continuous function, well then there must exist a point C in the domain such that f of c equals n. So here, for this number c, we have f of c equals n. And continuity is so important here. Let's break the continuity. If we take away the continuity, this does not work. So let me show you here. If we had a hole, so I'm going to put a hole in the graph right here. So right here in the graph, there's a hole. Okay. So now look, the theorem doesn't work anymore. Here, n is still a number in between, but I cannot find a number c that's, in the interval. So here, there's no function, so this doesn't work. I'd never get to c. And why doesn't this work? Because here we took out the requirement that the function be continuous. And here, when I put a hole in the graph, the function is no longer continuous. So for a continuous function, basically what this is saying is, for a continuous function, if I know n is in the range, if I know n is in the range, then there must be some input value that's going to map to that function. So, depending on the graph and what's happening, we might have more than one input that maps to the output capital M. Just depends on what the function is doing. But if the function's continuous, we will definitely at least have one input that'll map to that output. So at the end of the day, when trying to use intermediate value theorem, establishing that f of x is continuous is very important. And this is when we would use arguments such as it's a polynomial or it's a sum of continuous functions. We know root functions are continuous. That's when we would use that theorem regarding the types of, which families of functions we know are continuous and are not continuous. So I want to do two examples. The first example is a little bit kind of artificial. It's a little too straightforward. And the second example is a little trickier. That's more like the type of intermediate value theorem problem you might see. So this first example asks the question, does the function f of x equal to x to the fifth plus x cubed minus 1 have a root in the interval 0 to 2? So remember, when we're looking for a root, we're trying to find an x-intercept. Now, one very subtle point that you have to pick up on here is this problem is not asking us to find the root, only to prove that such a root exists. Okay, so when we're trying to find the root, we're trying to solve for basically an x-intercept. So we have this x-intercept problem here that we're trying to solve. But I just want to show the existence. I do not want to try and actually find the root, because for this problem, it's almost impossible. X to the fifth plus x cubed, minus 1. I don't think you can factor that easily. So here, it's very important that we understand we're not trying to find the root, just show that a root exists. So we will use the intermediate value theorem. And therefore, the first thing I do for the intermediate value theorem is make the comment that the function we're dealing with, x to the fifth plus x cubed minus 1, is a polynomial function, which implies it's continuous on any interval. Certainly 0 to 2, it's continuous for all reals. So now we can start to use intermediate value theorem. Intermediate value theorem, you know, we're able to show that there's a number c such that f of c equals capital N. So here the capital N that we want is 0. I want to show f of x equals 0 has a solution. I want to show there's a number c such that f of c equals 0. The intermediate value theorem allows us to find a number c such that f of c equals capital N. So here capital N is 0. If I can show our endpoints, you know, surround 0, if 0 is in between f of 0 and f of 2, then we can use continuity. Now calculating, f of 0 is -1, so it's less than 0. And f of 2, after you do the math, you get it's 39, so it's greater than 0. So if capital N here is equal to 0, then we've shown that capital N is in between f of 0 and f of 2. So capital N is in the range of this continuous function. And since it's a continuous function, by the intermediate value theorem, there must be an input that maps, that gets sent to this output. Because this proves capital N is within the range of our continuous function. So every number in between, because it's a continuous function, is being hit. So since f of x is continuous, by the intermediate value theorem, there's a number c in between 0 and 2. There's an input in the domain such that that input gets sent to n. F of c equals n, you know, capital N is 0. So what we're saying is f of c equals 0. Basically, we've shown that there is a root. We haven't found the root, but by using the continuity properties of the function, we're able to assert that, yes, there is a root. And so the next question is, how would we find the root? And so actually, we can use intermediate value theorem to answer that question. So this is not anything we're going to do in this class, but how would we find the root? Well, now I know that the root is in between 0 and 2. So I know the root is somewhere in this interval, 0 and 2. So I know when you plug in, you know, f of 0 is -1, so maybe it's down here, and f of 2 is 39, so maybe it's down here. So now what we do is we divide the interval in half and check the value of the function at 1. Here, f of 1 is 1 plus 1 minus 1, so 2 minus 1. F of 1 is positive. So now I know the root must be between 0 and 1. And so now I play the game again. You divide this root into 1/2, check the function value. If it's positive, then the root is between 0 and 1/2. If the function value is negative, then the root is between 1/2 and 1. And in this way, you can make the interval smaller and smaller and smaller until you get the tiniest interval that contains the root. And if the interval is small enough, that'll be a good approximation to what the actual root is. So this very simple theorem called the intermediate value theorem, combined with computers, gives us an incredibly powerful root finding method called the bisection method, which is just take the interval, divide it in half, check the endpoints. If the endpoints change in sign, the interval, the root is still in that interval, make the interval smaller and keep chasing the end, you know, where the x-intercept is. So this next example is basically the same as the previous example, except we have to do one extra step, okay? So it starts out asking us to show that the equation cosine x equal to x has a solution. It does not ask us to solve this. Show that the equation cosine of x equal to x has a solution. So I'm going to convert this into a root finding problem. If we have the equation cosine x equal to x, what I can do is take the x and move it over to the other side. Then we're trying to solve the equation cosine of x minus x equal to 0. So if I let f of x equal to cosine of x minus x, I'm back to trying to solve a root finding problem, but just with a different function. Instead of x to the 5th plus x cubed minus 1, I now have cosine x minus x. That's the function that I'm trying to find the root for. So now this is my function, and I want to show it has a root. It's basically now the same problem as before. There's only one issue. In the previous example, they gave us an interval. So here there's no interval. So what I'm going to do is I'm going to graph. I'm not going to graph this function. Okay, what I'm going to do is I'm going to graph cosine of x, and I'm going to separately graph x all on the same axis and just eyeball where the root is. So here, this graph right here, so for x, you can see is right here. And cosine of x, the graph for cosine of x you can see is right here. I'm trying to basically ascertain this, right? I want to find this value, or at least show that this number exists. You know, so this intercept is what we're looking for. But from the graph, I can just eyeball it and estimate just visually that the intercept is in between 0 and pi over 2, just using the graph. So based on the graph, I'm going to guess that there's a root between 0 and pi over 2. And so now I have an interval. Here in the previous problem, we were given an interval 0 to 2. In this example, I'm able to use the graph to figure out, here's a nice interval. Let's use the interval 0 to pi over 2. And so now I just need to check that 0 is in between these, right? So here, f of 0. So now in this function right here, I'm plugging in a 0 for x. So cosine of 0 would be 1 minus 0. So f of 0 is just 1, which is greater than 0. And f of pi over 2, again, I'm replacing this x right here with pi over 2. Cosine of pi over 2 is 0 minus pi over 2. So here, f of pi over 2 is negative pi over 2, which is less than 0. So basically, we've shown 0 is in between f of 0 and f of pi over 2. That is, 0 is in the range. And since of f, and since f is continuous by the intermediate value theorem, there must be at least one number c in the interval 0 to pi over 2, such that f of c equals 0. Now, if you follow the equations back, f of c is cosine c minus c, which is equal to 0. And you move the c over. So finally here, we get cosine of c equals c, which is exactly what we wanted to show is true. We wanted to show that this equation is in fact a true statement, that there is some number such that cosine of that number equals that number. And here we found this number c. You know, we've even gone one step further. We've even identified which interval it's in. We've shown that there's this number c such that cosine of that number is equal to the number. And this is all using continuity. So I'm going to let you think about that and think about continuity. And really this picture I think is very important. It helps to go back to this picture to understand how this is working. That if a number is in the range of a continuous function, because of the continuity, we should be able to find an input value for that range value. And it's, you know, continuity is huge. So that ends section 1.5. And so now I'm going to switch over to section 1.6. So I emailed out these slides on Sunday. So here's section 1.6. So this is basically the last set of techniques that we need to be able to deal with limits. And there's two types of limits we want to talk about here. So I want you to pay attention to the language and think about what's an infinite limit versus a limit at infinity. Okay, so we'll do infinite limits first, and then we'll probably finish up limits at infinity on Wednesday. So we start with a very important example. This is kind of a prototype example. Evaluate the limit as x goes to 0 of 1 over x. So now I want to be very careful. I want to say evaluate the limit of the two-sided limit. So I want to remember that this is a two-sided limit. So let me do this problem very meticulously by first checking the one-sided limits. So I'm going to send x to 0 from the right here. So we're starting with a positive number that's getting smaller and smaller and getting closer to 0. So here I have 1 over 10, which is 0.1, then 1 over 1. So here what you should notice is the denominator is getting smaller, but is positive. Then I did 0.01, 1 over 0.01 is 100, 1 over 0.001 is 1,000. Trend is the fraction is getting bigger and bigger and going to infinity as the denominator gets closer and closer to 0. And again, if we approach x going to 0 from the left, we have basically the same thing, except it's going to negative infinity. Here, 1 over negative 10 is negative 0.1, 1 over negative 1 is negative 1, 1 over negative 0.1 is negative 10, and you see it's blowing not up, but down to negative infinity. So we've found these one-sided limits, and of course the graph bears that out, right? So you remember the graph here shows exactly this happening right here in this section. When we approach 0 from the right, the graph blows up to infinity, and when we approach 0 from the left, the graph goes to negative infinity, as you see down here. So we have the one-sided limit as x approaches 0 from the right is plus infinity. The one-sided limit as x approaches 0 from the left is negative infinity. Plus infinity is not the same as negative infinity, thus the two-sided limit does not exist. So I think a very common mistake that some students might make is some students might write that the two-sided limit equals plus infinity. And of course, that would be wrong. The two-sided limit is a D and E, so this would be wrong. What's correct is the two-sided limit does not exist. Now be very careful. Right here, when I say the limit equals plus infinity, I'm not saying the limit exists. This is, the limit here does not exist. When I say the limit as x goes to 0 from the left is negative infinity, again, this limit does not exist. Here, I don't want to write D and E here. In math, we want to be as precise as we can be. So here I can tell you exactly in what fashion the limit doesn't exist. I can exactly describe how it's not existing. Remember, plus infinity is not a number. Plus infinity is a behavior. When I write limit as x goes to 0 from the right of 1 over x equals plus infinity, what I'm saying is that the limit gets larger and larger and larger forever without bound and doesn't stop getting bigger. The limit does not exist. It diverges to plus infinity. Again, when we say the limit equals negative infinity is not a number. That's not the number 8 that's taking a nap on its side. Negative infinity is a behavior. When we say the limit's negative infinity, what we're saying is the limit goes down, gets larger and larger with a negative sign in front of it forever. It diverges to negative infinity. And here, this, of course, is also does not exist, but a different kind than the other two. Here we're saying the limit from the left doesn't equal the limit from the right. So in all three cases, the limit does not exist. And here we get a very important rule for our limits. In a one-sided limit, if we get the form non-zero number over 0, then the limit is either going to be plus infinity or minus infinity. The fact that we're looking at a one-sided limit is important. So let me apply this rule to this problem right here. So for example, look at this limit here. If we apply the limit, so if I plug in the x, remember I always say the first rule of limits is to plug in. So I plug in an x, I get 1 over 0. So that's my non-zero number over 0. And now check the SIGN of 1 over x. 1 over x, as x approaches 0 from the right, is always positive. That's why this is a plus infinity. Again, if you look at this other one, let's just try to do the limit directly. Plug in the 0. When I plug in 0, I get 1 over 0. That's my non-zero number over 0 form. So now I know the limit is either plus infinity or minus infinity. Check the SIGN. 1 over x, for x approaching 0 from the left, is negative. And that's why there's a negative infinity right here. For this limit, if you try and plug in the limit directly, listen, you get 1 over 0. But now you have to say, wait a minute, this is a two-sided limit, and I need to check the one-sided limits. So that's the thing. That's why I think this is a very important example. So if you get this down, you know, it covers a lot of scenarios. So this is our new limit rule, that if you get non-zero number over 0 in a limit, in a one-sided limit, then it's either plus infinity or minus infinity. We have to check the SIGN by plugging in numbers. So where the limit is plus or minus infinity, that line is called a vertical asymptote. So x equal to a will be called a vertical asymptote if the limit of f of x as x approaches a from the right is plus or minus infinity, or if the limit approaching a from the left is plus or minus infinity. One or the other, they don't both have to be true. If they're both true, that's great, but they don't both have to be. Just one or the other has to be true. And where we have a vertical asymptote, you know, we're also going to have an infinite discontinuity. And for a rational function, functions with polynomials in the numerator and denominator, the vertical asymptotes typically occur in the roots of the denominator. And so here I have an example here. It's a strange example. It does involve a rational function, but it's actually technically a piecewise defined function, right? That's a rational function. And here we're asked for the domain as well as the vertical asymptotes. So I purposely did this because it's a weird problem. Here the domain is all real numbers. There's no problem. If x is not equal to 0, it's defined. If x is equal to 0, it's defined. So it's defined for all real numbers. However, I'm looking for vertical asymptotes. So I'm looking for any place the limit might blow up to infinity. And we know for a rational function, the roots of the denominator are potential vertical asymptotes. The root of the denominator here is 0. So I want to check the limit as x goes to 0. And so here, let me do this in 2 steps. So here, first try to apply the limit. When I try to apply the limit, plug in the number, I get 1 over 0. So immediately I can conclude this is a number over 0 type indeterminate form. Now, because this is a two-sided limit, I should check the one-sided limits, but in this case, we get a break. In this case, we know that 1 over x squared is always positive if x is not equal to 0. Since 1 over x squared is always positive, in this case, I can skip the one-sided limits and I can evaluate the two-sided limit directly. Is it wrong to look at the one-sided limits? Absolutely not. If you do the one-sided limit, you'll get the limit from the right equals plus infinity and the limit from the left equals plus infinity. So the two-sided limit equals plus infinity. Now be careful, I'm not saying the limit exists. When I write the limit equals plus infinity, we're saying this is a type of does not exist. Except we're being more specific. We're telling you exactly the limit just gets bigger and bigger and bigger and bigger forever. So here, yeah, there is a vertical asymptote and infinite discontinuity at x equal to 0. The graph looks like this, and I wanted to do a weird example. So here, even though the function is defined for all x values, it has a vertical asymptote and an infinite discontinuity, and it's crossing its own vertical asymptote, right? So I just wanted to do this weird example, but you know, all the math makes sense. It satisfies all the rules we need. So there is a vertical asymptote at x equal to 0 and an infinite discontinuity. So let me do a problem here. Here, if you look at this, we have x minus 2 over x squared minus 4. And so the roots here, as you remember, I can factor this as x minus 2 times x plus 2. So I'd like to look at the limit at the two different roots. As x goes to 2 and as x goes to minus 2, and I'd like to, just say what's the difference here? Because here we have two drastically different behaviors. So the first thing, it's a limit problem, as opposed to a derivative problem or integral problem. For a limit, the first thing I'm going to try and do is plug it in. In this case, when I plug it in, we actually get the indeterminate form 0 over 0, not number over 0. So here you have to remember, okay, what do I do for 0 over 0? Either factor and cancel, multiply by the conjugate, try a squeeze theorem. In this case, based on the form, because we know we can factor the denominator, let's try and factor the denominator. And then the next step would be, we can cancel. I can cancel x minus 2 upstairs and downstairs. And now apply the limit. As x goes to 2, just plug in 2 and see what we get. When we plug in 2, I get 1 over 2 plus 2, or 1/4. So here, the limit exists, but the function is undefined at 2. At 2, if you plug in 2, the function is 0 over 0. So this is one of those scenarios where the limit exists, but the function is not defined at the point. We'll see this is a removable discontinuity. Even though 2 makes the denominator 0, 2 is not a vertical asymptote in this case. That's the point of this part here. And I had to check it with the limit. The limit existed. The limit wasn't plus or minus infinity. Look at this next problem here. For going to -2, the other root. First, if I try and plug it in directly, just try and plug it into the two-sided limit directly. Actually, here I factored it and canceled it and then plugged it in. It doesn't really matter. You can cancel, you can simplify it and plug it in or not. It doesn't matter. Either way, you're going to get number over 0. So here I plug in. Upstairs, we have just 1. In the denominator, minus 2 plus 2 is 0. So I get 1 over 0. Now be careful. I don't say here the limit's plus or minus infinity. Here, this is a two-sided limit. So now I say, okay, let me be careful. Let me check the one-sided limits first. And so now I'm looking at the limit as x approaches -2 from the left. And so if you look on an x-axis, here's -2. I want to approach, so here's the left. It really helps to draw these number lines. I want to pick a number to the left of -2, but very close. So I'm going to pick like -2.1. Plug in -2.1 right here. This whole thing is negative. Here, the form is a number over 0 when you plug it in, and it's a one-sided limit. So this is either plus or minus infinity. And because this is negative, when you plug in a -2.1, my answer for the limit here is that it goes to minus infinity. For the other limit, I'm looking at the limit approaching -2 from the right. So again, it helps to look at the number line. I'm approaching from this side, from the right side. So for example, I'm going to pick very close, right? Very close, but on the right, -1.9. Take -1, if you try to do the limit, the one-sided limit, you get 1 over 0. You get number over 0. So I know it's plus or minus infinity. Now take a number to the right, whoops, and plug it in right here. Take a number to the right of -2, like -1.9. This is on the right side right here. Plug it in. This is positive, so I have a plus infinity. And again here, the one-sided limits don't agree, so the two-sided limit is a DNE. It's really important that you get how I calculated each one of these limits, using this this new form here, number over zero, in a one-sided limit, tells me it's plus or minus infinity. Now you plug in numbers to determine whether it's negative or positive. If it's negative, then the answer is negative infinity. If it's positive, then the answer is positive infinity. And here the two-sided limit, we don't forget our theory, the two-sided limit, is dependent on the one-sided limits. Here they don't agree, so the two-sided limit does not exist. So here we can kind of summarize what's going on at the two different points. So for this function, classify all points of discontinuity. So first of all, we know the domain is x can't be equal to plus or minus 2. So the function is not continuous at 2. It's not continuous at negative 2. Cannot be continuous outside of its domain. At x equal to 2, because the limit exists, but the function's not defined, we have a removable discontinuity. Here the limit exists, but the function is undefined. So that's your recipe for a removable discontinuity. At x equal to negative 2, since the limit are blowing up, to infinity and or plus or minus infinity here we have a vertical asymptote. And also vertical asymptotes are also an infinite discontinuity. So this example is to point out that the roots of the denominator aren't always asymptotes. In this case, one of the roots of the denominator was a removable discontinuity, and the other root of the denominator was a vertical asymptote. We ultimately have to do the limit to try and verify what's going on to be able to determine if it's a vertical asymptote, at least from a mathematical point of view, to be perfectly mathematically correct. So let me finish this slide here. So this is a limit at infinity. So I want you to now be very careful and go, what's that about? So here, in all the limits before today, we were sending x to a finite number. And now we're sending x to infinity or minus infinity. And so I want you to be very aware when you're doing limit problems. I want you to first go, oh, this is a limit problem. Am I sending x to a finite number or infinity or minus infinity? If you're not, those are two different categories. For limits where x goes to infinity or minus infinity, we want to treat those slightly different. We have a different rule here. So here, let's do the limits just by plugging in points. So I'm going to make the denominator here larger and larger. And when you make the denominator larger and larger, the fraction gets smaller and smaller. So as x goes to infinity, it seems like the limit goes to 0. And similarly, if you go x goes to negative infinity, as I make the denominator larger and larger, the fraction gets smaller and smaller and basically converges to negative 0, but negative 0 equals 0. So here's my, the graph bears it out. So here in the graph, if you look at the tail portion here, so we call this the tail of the graph, that's x going to infinity or x going to negative infinity, you can see the function approaches 0. So we conclude the limit of 1 over x as x goes to plus infinity is 0, and the limit of 1 over x as x goes to negative infinity is 0, and I'll stop right here. This is a new limit rule that I'm going to pick up here next time. Basically, in a limit, if you get the form number over infinity in a limit, that limit is going to be 0. Okay, so I will pick it up here next time. We will talk about limits at infinity next time and do a bunch of examples and finish up section 1.6.